In Chapter 6, Section 8, we talk about complex numbers, and we are now ready to delve into Standard 6 and Standard 5 from the California State Standards, and that's the students need to know how to add, subtract, multiply, and divide complex numbers. Obviously, we're going to have to tell you what that is first. And then you need to demonstrate knowledge of how real and complex numbers are related arithmetically and graphically. We're going to do that in this lesson. And in particular, we need to know how to plot complex numbers as points on a plane. And so our objectives, we need to add complex numbers, subtract complex numbers, multiply complex numbers, divide complex numbers, graph complex numbers in a complex plane, and identify how complex numbers are related to the other number systems that we've learned so far. So, what is a complex number? Well, if we take a real number and the imaginary numbers that we've learned in our previous lesson together, that forms a set of complex numbers. A complex number is written in the form a plus bi, where a and b represent real numbers. The a represents the real part of the complex number, and b might represent the imaginary part of the complex number. And what we can do is we can look at the set of complex numbers in this little illustration. So far again, from kindergarten to today, you started with the counting numbers. You added 0 to get the whole numbers. You added the negatives to get integers. We added the fractions to get the rational numbers. Numbers kind of like pi and the square root of 2, we were the irrational numbers. And in a few lessons ago, we said that included everything we knew at that point, which was the real numbers. In our most recent lesson, we learned imaginary numbers. So now if we take real numbers and imaginary numbers together, put them in the form a plus bi, that gives us a complex number. And unless you're going to go further on into math, this is the last number system that you will need to learn. And what we need to do is several things with complex numbers, starting out with how do we know when two complex numbers are equal. So for equality of complex numbers, a plus bi, that is equal to c plus di if and only if a and c are the same number and b and d are the same number. How do we add complex numbers? Well, we add the real portions, a plus c. We add the imaginary portions, bi plus di, and we simplify that. How do we multiply complex numbers? Well, a complex number is a binomial, so essentially we FOIL it out. The firsts, a times c, the outsides, which is ADI, insides, BCI, and lasts, BDI squared, which remember that I squared becomes negative 1, so that's how we end up with negative BD. So let's look at simplifying some of these situations. And in most of these situations, we add the real parts, so 3 plus negative 2. We're going to add those together. We're going to add the imaginary parts, so 4i plus negative 6i. 3 plus negative 2 is 1. 4 plus negative 6 is negative 2i. And that's the sum of those two complex numbers. Instead of subtracting complex numbers, I suggest that we add the opposites so we don't make a careless mistake. And then it's the same as adding. So the 7 plus the negative 3 and the 2i plus the 6i. So 7 plus 3 is 4, 2i plus 6i is 8i. So adding or subtracting complex numbers is fairly straightforward. Multiplying again is straightforward. It's just FOILing like we learned in chapter 4, but remembering that I squared is the same as negative 1. So doing the first, 2 times 5 is 10. Outsides, 2 times negative 6i is negative 12i. Insides, 3i times 5 is 15i. Lasts, 3i times negative 6i is negative 18i squared. Collecting like terms, the negative 12i plus 15i is 3i. Remember that I squared by definition is the same as negative 1. Negative 1 times negative 18 is positive 18. 18 plus 10 is 28 plus our 3i. So that's the product of our two complex numbers. Let's square our complex numbers. First of all, remembering how to square a binomial. You take the first number, which in this case is 2, and square it. Multiply these two, so that's 2 times negative 4i, and then double it. Take the last number including its sign and square it. That's what the formula said we learned in Chapter 4 for squaring a binomial. So 2 squared is 4. 2 times negative 4i is negative 16i. Negative 4 times negative 4 is 16. I times I is I squared. Don't forget that I squared represents the quantity negative 1. 16 times negative 1 is negative 16. Negative 16 plus 4 is negative 12. So we have negative 12 minus 16i. So that was squaring a complex number. When we have complex conjugates, interesting thing happens. So let's do this. First, 2 times 2 is 4. Remember that when they're conjugates, the outsides and the insides will drop out. In this case, that would be negative 6i and positive 6i. That subtracts to 0. So we do the first and the last. The last gives us negative 9i squared. Remember that I squared is negative 1. Negative 1 times negative 9 is positive 9. And 4 plus 9 is 13. So again, when we have complex conjugates, just like when we had binomials containing radicals that were conjugates, we multiplied them and all the radicals disappeared. Here, when we multiply complex conjugates, we get a real number without the imaginary portion, which is very important in simplifying the next example. In this case, since we have I in the denominator, we must get rid of it, but it's part of a binomial. So as we learned in this chapter, when we had binomial radicals in the denominator, we must multiply numerator and denominator by the conjugate. So in the numerator, first, 2 times 2 is 4. Outside gives me 6i. Inside gives me negative 2i. Last in the numerator gives me negative 3i squared. Denominator, they're conjugates, so we do the first, which is 4. And the last, which is negative 9i squared. In the numerator and denominator both, I squareds are the same as negative 1. In the numerator, 6i minus 2i is 4i. And then what we have with our negative 1 times negative 3 is positive 3, plus 4 is 7 plus 4i. In the denominator, negative 1 times negative 9 is positive 9, plus 4 is 13. And we no longer have a complex or imaginary number in our denominator. That's our answer in simplest form for our complex answer. Alright, now be careful about problems like example 4. It seems deceptively easy. When we say find the reciprocal of 2 minus I, quite often students just say, well, that's 1 over 2 minus I, which is the right way to start the problem. But we need to finish it, and we cannot leave an imaginary number or a complex number in our denominator. So again, we must multiply numerator and denominator by the conjugate of the denominator. In the numerator, that's 2 plus I. In the denominator, we do the first, that's 4. The last, which is negative I squared. Don't forget that I squared is the same as negative 1. And 4 minus a negative 1 is 5. So it seems a little strange, but 2 plus I over 5 is the reciprocal of 2 minus I in simplified form. Alright, well, what we need to move on to next is something that's not in our textbook, but it's in the state standard, so we still need to pay close attention to it. And that's representing complex numbers in a coordinate plane. Instead of a plus bi, sometimes we call them x plus yi, and that corresponds to an xy point on the plane. Now, because we're representing complex numbers, we no longer call it the coordinate plane, but we call it the complex plane. The horizontal axis represents the real numbers, or the real axis. Vertical axis is called the imaginary axis. So here's what the complex plane might look like. Real numbers horizontally, imaginary numbers vertically. And this thanks to Dr. Joyce and his website for this information, since again it was not in our textbooks. Now we need to consider a few things here before we graph. Real numbers are just special cases of complex numbers. It's x plus yi, where the y coefficient of the imaginary term is 0. And we can graph those on the real axis, which is the horizontal axis. Numbers that are purely imaginary, the vertical axis, can be done similarly, considering the real part, x here, as 0, and we can just plot the yi portion. So what we'd like to do is graph the following numbers on the complex plane. And so 4 is a complex number even though it's a simple counting number. It's contained in the complex numbers. 4 is located right here on the real axis. Its only component is 4. Then to graph negative 2i, its real component is 0, so it goes nowhere left and right. We go down 2i on the imaginary axis, plot that point, and label it. 4 plus 2i, we start at the origin, 0, 0. We go right 4. So for 4 plus 2i, we start at the origin. We go 4 units on the real axis, and then up 2i on the imaginary axis. Plot our point, label it, so that point in complex plane space represents the complex number 4 plus 2i. Then negative 4 minus I, again we start at the origin, go negative 4 on the real axis, down I on the imaginary axis, plot that point, label it negative 4 minus I. And then the next one, negative 2 plus 2i, start at the origin, go negative 2 on the real axis, up 2i on the imaginary axis, plot the point, label it, that represents negative 2 plus 2i. So graphing complex numbers gives us a geometric way to represent complex numbers, which is part of the Algebra 2 State Standards number 5. In the beginning of the lesson, we represented them just algebraically as a plus bi, or in this case we're calling it x plus yi. Addition can also be done graphically. We've done that just algebraically in the beginning, but geometrically addition can be represented on the complex plane. If we're to add 3 plus I, and we're adding to that the complex number negative 1 plus 2i, we can do that on the complex plane. So first let's locate where 3 plus I is. Start at the origin, go 3 on the real axis, up positive I on the imaginary axis, plot that point Z, which we're calling it, which is the point 3 plus I. And then we're going to locate negative 1 plus 2i, so we start at the origin, go left negative 1 on the real axis, up 2i on the imaginary axis, plot that point, label it, there is negative 1 plus 2i. Now algebraically we know when we add negative 1 plus 3 we get 2, when we add 3i plus 1i we get 3i. If I were to plot that, 2 on the real axis, up 3i on the imaginary axis is that point, labeled 2 plus 3i. And what we notice is that all 4 corners, including the origin, the negative 1 plus 2i, the 3 plus I, and our solution, their sum of adding the two complex numbers, 2 plus 3i, form a parallelogram. And so this brings up our next point, which is the parallelogram rule for adding complex numbers. In that previous example, the 4 complex numbers, including the origin 0, 3 plus I, negative 1 plus 2i, and the sum 2 plus 3i are corners of a parallelogram, and that's generally the case. So to find where in the complex plane the sum of 2 complex numbers are located, we can draw lines from 0 to each complex number and then complete a parallelogram, and that last vertex of our parallelogram will be the sum of the 2 complex numbers. So let's use that rule to graphically find the sum of 2 complex numbers. And let's take some easy ones like 3, which is a complex number, 3 plus 0i, and then 0 plus 2i. So starting with 3, that's 3 units on my real axis, 0 units on my imaginary axis, plot the point. And then 2i is 0 units on my real axis, 2i units on the imaginary axis. Let's draw the lines from the origin to each of those complex numbers. And then if we were to complete the parallelogram by drawing a line the same length parallel to this vector and drawing another line parallel and the same length to this vector, that gives us our vertex here of the parallelogram, which happens to be the point 3 plus 2i, and that's what we get. That's our solution when we take 3 and add 2i to it. So this example illustrates the parallelogram rule for adding 2 complex numbers with a nice, simple example. Alright, let's graph the following complex numbers for example 7 and then use the parallelogram rule to find and graph the sum. So let's look at 2 minus 2i. So it's 2 units on the real axis, negative 2i units on the imaginary axis. Plot that point. 1 plus i, let's locate that. So that's 1 on the real axis, up I on the imaginary axis, label that point. Let's draw our lines from 0, the origin, to each complex number. Let's complete out the parallelogram. So we need a side parallel to this side, the same length, and another side parallel to this side of the same length. And that gives us our parallelogram. And in this fourth vertex, we have the sum of 1 plus I added to 2 minus 2i. Sorry about that. And we all know that 1 plus 2 is 3. 1i minus 2i is negative I. And that's where this point is located on the complex plane. That's located at 3 units for the real parts and negative I units for the complex parts. So again, thanks to David Joyce, Clark University, for the information on complex numbers. If you need to find out more information, you can go to his website. So that's complex numbers, how to know when they're equal or equivalent, how to add, subtract, multiply, divide, and how to graph the representation of a complex number and use the parallelogram rule to find the sum of two complex numbers.